Welcome to an organic chemistry video lecture. We're looking at functional group chemistry. The focus of this piece of video lecture is alcohols. Our essential understanding continues to be that the structure, bonding, and chemical reactions involving functional group interconversions are key strands in organic chemistry. Basically, in organic chemistry, we look at chemical reactions of organic compounds. Our objectives, we're going to write some equations for more combustion, but this time of alcohols. We're going to predict the products of oxidation of alcohols, and then we're going to predict the products of esterification reactions of alcohols and carboxylic acids. So first up, let's remind ourselves what even is combustion. So complete combustion of alkanes is going to form carbon dioxide and water. So quick review, how do we write an equation for the complete combustion of methane? Remember, meth is one carbon, so we're going to have CH4. Combustion is always adding oxygen. The products are going to be carbon dioxide and water. To balance this, I'm going to add 2 waters, 2 oxygens. I now have a balanced equation. Alcohols, the complete combustion of alcohols is also going to produce carbon dioxide and water. So let's look at methanol. So again, meth is 1 carbon. So I'm going to add 1 carbon. It's going to have a hydroxyl group in order to make it that alcohol. Fill in carbon with some hydrogens to fulfill that octet rule. And here we have methanol. So methanol is going to be CH3OH. We're going to add oxygen again, and we're going to make carbon dioxide and some water. To balance this out, I still need 2 waters. But here's where things get a little bit interesting, because I do have this oxygen here. I don't need quite as much oxygen here. And so I'm going to say 1.5 moles of oxygen gas needed to combust this 1 mole of methanol. So you might be thinking, well, we need less oxygen here. We need more oxygen here. Perhaps alcohols are better for us to use as fuel sources. Just because we don't need quite as much oxygen, we have easier times getting that oxygen so we can get that complete combustion to happen. And in terms of oxygen required, you're right. This is a little bit more, I don't know. We're at a lower risk of incomplete combustion. But what is less good about its combusting alcohols is the amount of energy that is released. So delta H, this is the change in enthalpy, how much energy is released. Per mole of methane, we're going to get 890 kilojoules per mole. With methanol, we're only going to get 726 kilojoules per mole. You might be thinking, that's not that much less. Well, yes, but if we convert our moles to grams, so 1 mole of methane is going to have a molar mass of about 6 grams. 1 mole of methanol has a molar mass of about 32 grams. And so we need twice as much mass of methanol to get slightly less energy. And so we're actually better off keeping with our alkanes for fuel sources. Alcohols can also be oxidized. Remember that oxidation is the loss of electrons or protons, hydrogen ions, but Leo says GER, lose electrons, oxidation, gain electrons is reduction. So we're looking at taking some electrons and hydrogens away from alcohols. The reaction is going to depend on the classification of that alcohol, whether it's primary or secondary or tertiary. Let's remind ourselves, what does that even mean? We're going to do that by drawing some alcohols. So 2-propanol, remember that meth-eth-prop, prop has 3 carbons, meth-eth-prop. I'm going to put my hydroxyl group on carbon number 2 to make this 2-propanol. We're going to fill in everything else with hydrogens to fulfill the octet rule. Hydrogen all over the place. Good. So I'm going to call propanol a secondary alcohol because notice that the hydroxyl group is bound to a carbon that is bound to 2 other carbons. So we're going to call this guy secondary because we've got 1 carbon, 2 carbons. Let's draw ethanol. So meth-eth, we need 2 carbons, meth-eth. I'm going to put that hydroxyl group at either end. It doesn't even matter. We're going to have ethanol regardless. We don't need to add a number because it doesn't matter, right? Whether I put hydroxyl group here or if I put hydroxyl group here, I would still call that carbon number 1, right? Right. So let's look at what this guy is bound to. So the hydroxyl group here is bound to a carbon that is bound to only one other carbon. That makes ethanol a primary alcohol. Last but not least, let's look at 2-methyl-2-butanol. You can probably already guess that this is going to be tertiary because we haven't looked at a tertiary alcohol yet. Meth, eth, prop, bute. I need 4 carbons to get that butanol. Meth, eth, prop, bute. I'm going to put a methyl group on carbon number 2. Remember that meth is 1 carbon. So I'm going to put a carbon branch, just 1 carbon on carbon number 2. I'm also going to add the hydroxyl group to carbon number 2 because it's 2-butanol. So the hydroxyl group is also going to be on carbon number 2. Everything else gets some hydrogens to fulfill octet rules. So many hydrogens. Good. So now let's find that hydroxyl group. Hydroxyl group is here. Hydroxyl group is bound to a carbon that is bound to 1, 2, 3. 3 carbons. That makes this guy tertiary. Tertiary alcohol. Primary alcohol, hydroxyl group on a carbon bound to only 1 other carbon. Secondary alcohol, hydroxyl group on a carbon bound to 1, 2 other carbons. All right, so now we're going to talk about oxidation of primary alcohols first. So we can oxidize steal electrons and protons away from alcohols by using one of 2 different reagents. So we can use acidified potassium dichromate or acidified potassium permanganate. Potassium dichromate starts orange. Once it oxidizes the alcohol, it turns green, which is pretty cool. Potassium permanganate starts purple. Once it oxidizes the alcohol, it's going to be colorless. Please note that in chemistry, we do not say things are clear. We call them colorless. If you are full-blown IB world, then you can use the British spelling of colorless. Kind of fun. So acidified potassium dichromate, acidified potassium permanganate are our options for oxidizing the alcohol. They are oxidizing agents. They are reduced when the alcohols are oxidized. When we're looking at primary alcohols, kind of like this guy is ethanol, meth, eth. I've got my hydroxyl group on a carbon that is bound to only 1 other carbon. That makes this a primary alcohol. So here, if I'm using my potassium dichromate, it is acidified. I need some extra H's in order to balance out my redox reactions. What's going to happen is this. Where that hydroxyl group was, we're going to take away a hydrogen, and then we're going to double bond to that oxygen. So I still have 1 hydrogen left. That hydroxyl group is now just a double bonded oxygen. Because I have this double bonded oxygen at the end, this carbonyl group is going to make this an aldehyde because carbonyl is at the end of the compound. This is now ethanal. If I want to keep the ethanal, then I have to distill that ethanal out of the reaction mix. So remember that distillation, we're going to warm it up. We're going to condense it back so that we have that ethanal removed, isolated from the reaction mix. I can have an aldehyde. But if I don't want an aldehyde, if I want instead a carboxylic acid, then I'm not going to distill, but instead I'm going to heat it and mix it. We're going to call that reflux. So I'm going to keep heating and mixing and heating and mixing. And then we're going to further oxidize that alcohol into a carboxylic acid. So we knock off an H, we double bond to the O, but then we add another OH in there. So a single bond to that OH. So we're going to go from alcohol to aldehyde, further oxidizing to that carboxylic acid. I'm going to call this guy 1,2-meth-ethanoic acid. Again, primary alcohols, we can oxidize them using acidified potassium dichromate or acidified potassium permanganate. Potassium dichromate is going to go from orange to green. Potassium permanganate is going to go from purple to colorless. The alcohol, if I let it be oxidized just a little bit, is going to be an ethanal, or an aldehyde with that carbonyl group at the end. If I continue to mix and heat under reflux, then we can get all the way oxidized to a carboxylic acid. Good. All right, let's look at a secondary alcohol now. let's say my secondary alcohol in this instance, I have isopropyl alcohol, also known as meth-eth-prop 2-propanol. So meth-eth-prop 2-propanol or isopropyl alcohol. Secondary alcohol because the hydroxyl group is bound to a carbon that is bound to two other carbons. So this is a secondary alcohol. I'm still going to use acidified potassium dichromate. It's going to go from orange to green. I'm still going to use my other option, acidified potassium permanganate, which will go from purple to colorless. But because my hydroxyl group is here in the middle of the compound, I'm not going to make an aldehyde. Instead, we're going to get that same carbonyl group. It's still a carbonyl group, just like I had in the beginning of oxidizing my primary alcohols, but because the carbonyl group is in the middle of the compound and not at the end, I have a ketone, not an aldehyde. Double bonded O in the middle of the compound is a ketone, not an aldehyde. This is the end of the line for our secondary alcohols. We cannot further oxidize this guy like I could those primary alcohols. So to review, primary alcohols, we can go from an alcohol to an aldehyde and then to a carboxylic acid. My secondary alcohols, we can oxidize these guys to ketones. That's the end. There is not a second step. There's no distillation or reflux required. What about our tertiary alcohols? Tertiary alcohols, nothing happens. Nothing happens. These guys just won't even react. So my acidified potassium dichromate will go from orange, it'll stay orange because nothing happens. My potassium permanganate will go from purple to it'll stay purple because nothing happens. So tertiary alcohols, no reaction, nothing's going to happen, super boring. Right, whatever, it's okay. Sometimes things need to be boring. Now we're going to look at some esterification reactions. So when I add an alcohol and a carboxylic acid, alcohols plus carboxylic acids, super cool thing happens. So I'm going to take this OH group off of my carboxylic acid. I'm going to take the H off of the alcohol. These guys combine to make water. Because I'm pulling water out of this molecule, I call it a condensation reaction. I can also call it dehydration synthesis. In IB world, condensation reaction is more common. In AP world, dehydration synthesis is more commonly used. So I'm going to pull, again, I'm going to pull this OH and this H out and I get water. What I'm left with is this carbon that is missing a bond and this oxygen that is missing a bond, and they're going to find each other. So that oxygen and that carbon are going to bind to each other. What this looks like, so I have COOH, COOH. Over here I have OCHHH. I have OCHHH. Look what we've got, my friends. We've got ourselves an ester. So we call this esterification because I have literally formed an ester from an alcohol and a carboxylic acid. Good. All right, let's do another one. So let's do ethanol plus ethanoic acid. Ethanol plus ethanoic acid. Ethanol looks like this. Meth, and there's my alcohol group, and I've got H's all around. My ethanoic acid. So I'm going to go ahead and draw my carboxylic acid group, the carboxyl group here on the left. I'm going to have that C, we're going to have a double O, we're going to have an OH. And then because it's ethanoic, meth-eth, I have two carbons. So there's carbon number 1, meth, carbon number 2, F. And then we're going to fill in hydrogens to fulfill that octet rule. So once again, I'm going to steal the OH from the carboxylic acid. I'm going to steal an H from the alcohol. These guys are going to form water, 2 H's and an O. We're going to make some water. What's going to happen? The oxygen here is going to bind to the carbon here. They're going to find each other since they're missing those bonds that they used to have. What that's going to look like, of course, we have water and we're going to have 2 carbons and an oxygen. 2 carbons and an oxygen. We're going to have those hydrogens around our carbons, of course. And then here on the other side, I have carbon double O, and then carbon 3 H's, carbon 1, 2, 3 H's. So this part that used to be the alcohol is here. This part, my carboxylic acid, is here. And what do I form in the middle? That ester. So here's our ester group in the middle. So once again, esterification. I'm going to call this guy 1, 2. That's going to be S. Ethyl 1, 2. Ethanoate. Ethyl ethanoate. Good. All right, we did it. So objectives met. We wrote equations for complete combustion of alcohols. We predicted the products of oxidation of alcohols. It depends on the classification. Primary alcohols, we can make an aldehyde and then perhaps a carboxylic acid. If I have a secondary alcohol, we're going to make a ketone. If I have a tertiary alcohol, there's no reaction, nothing happens. And then we looked at alcohols and carboxylic acids. They can combine to make esters, esterification. Good work today, my friends.